Welcome to The Explainer. Today, we're taking on a concept that honestly terrifies a lot of computer science students. I'm talking about optimal binary search trees. But hey, don't worry, we are going to break down this seemingly math-heavy topic into a really intuitive, visually driven story. We're going to see exactly how dynamic programming elegantly solves what looks like an absolutely impossible puzzle. So think about this for a second. If you have a million items sitting in your database, how do you arrange them for instant searching? You definitely don't want to be wasting computing time looking for things that might not even be there, right? It's a huge, real-world problem for databases and search engines everywhere. Here's how we're going to break it down today. We'll start with the secret to fast searching, move on to a retail store analogy, calculate the search cost, tackle the too many trees problem, see how dynamic programming comes to the rescue, and finally build that optimal tree. All right, part one, the secret to fast searching.
First up, we really need to understand the basic mechanics of how keys, which are really just your data points, are arranged to speed up the retrieval process. You're probably familiar with the binary search tree. It's this brilliant data structure where all smaller keys are placed on the left side of a node and all larger keys go to the right. If you're searching for a number, you just ask the system, hey, is it smaller or larger than the current node? The number of comparisons you need depends entirely on the number of levels, meaning, quite simply, a shorter, shallower tree equals a significantly faster search.
Moving right along to part two, the retail store analogy. Now, searching isn't just about finding things. It's also about figuring out when things aren't there. To really grasp successful and unsuccessful search probabilities, let's just imagine you're managing a physical retail store. A successful search is when a customer finds an item you actually stock. Obviously, you're going to keep those high-demand, high-probability items right on the front counter for instant access. But an unsuccessful search happens when a customer asks for something that's totally out of stock. If you have to walk all the way to the back stockroom just to verify it's not there, you waste a ton of time. In our binary tree, we call these stockroom dead ends dummy nodes. And the reality is, both finding a popular item and verifying an item is completely out of stock cost you valuable time. Which brings us to part three, calculating the search cost. Now that we have that retail analogy in our heads, we have to mathematically calculate the true cost of operating our database store. So how do we run the numbers? First, for successful searches, you multiply the probability by its level. Level 1 takes one comparison, level 2 takes two, and so on. But, and this is absolutely crucial, for unsuccessful searches, those dummy nodes actually stop one level earlier. Because we terminate the search the exact moment we hit a dead end, we don't actually do a comparison on the dummy node itself. So we multiply their probability by their level -1. Finally, we just sum up all those values to find our total search cost. And that right there is our ultimate goal. We want the specific layout, the exact arrangement of keys that minimizes this total search cost formula. But actually finding that perfect arrangement, well, that introduces a massive roadblock. Enter part 4. The too many trees problem. Let's talk about the sheer, overwhelming volume of possible tree combinations. This is basically the main villain of our story. Get this, if you have just 4 keys, literally just 4 items to organize, there are already 14 different possible binary search trees you could draw. You'd have to calculate the cost for all 14 just to find the best one. The mathematical formula for finding the number of trees is a Catalan number. 2n choose n divided by n plus 1. Now, don't worry too much about the math itself. Just know that the possibilities scale astronomically. Extrapolating this to tens, hundreds, or millions of keys makes brute force checking literally impossible. No computer on Earth could draw every single tree to check the cost. Which means we need a really clever detective to crack this case. And here is part 5, dynamic programming to the rescue. This is our hero. Dynamic programming is essentially the ultimate cheat code to bypass that impossible brute force method. Instead of building giant, complete trees and checking every single one, dynamic programming systematically solves the issue by finding the answers to tiny subproblems first. We calculate the weights, we find the costs of small combinations, and we record which route gave us the lowest cost. Then, we just use those small answers to build slightly larger answers and we keep going. Here's how we actually execute this. We use a tabular grid. We start right at the top, where the difference between keys is 0, literally just analyzing a single dummy node. Then we slowly expand our knowledge outwards to a difference of 1, analyzing small subtrees, then a difference of 2, and so on. We are literally building our knowledge base from the ground up. And it is incredibly efficient. To find the new weight of a slightly larger subtree, we don't need to recalculate the whole shebang. We simply take the previous weight we already saved in our table and add the successful and unsuccessful probabilities of the newly added key. So how do we find the cost? Well, we isolate the process. For any small subproblem, we try out every valid key, which we call k, as a potential root. We take the left subtree cost, add the right subtree cost, and add the total weight. We test all the options, but we strictly save only the absolute lowest total cost in our vault. We try everything indirectly, without ever having to draw a single massive tree. Finally, part 6, building the optimal tree. With our dynamic programming table completely filled from 0 all the way up to our total number of keys, we can finally assemble our masterpiece, and we don't have to guess. We just follow the assembly rules. We look up the final recorded root for the entire dataset in our table. Say the table tells us the best root is key number 2. Great, 2 is our top node. Everything to the left of 2 becomes a new subproblem, and everything to the right becomes another. We just look up those subproblems in our table to find their optimal roots. By just following the breadcrumbs we left for ourselves in that root table, we perfectly construct the optimal binary search tree piece by piece. Honestly, it is so incredibly satisfying when it all comes together. We completely bypassed millions of calculations using a simple table that built upward from 0. Now that you've seen how a dynamic programming table can tame astronomical complexity and map out perfect efficiency, I challenge you to think about this. What other impossible algorithmic mountains can this cheat code help you climb? Where else might it save your database? Thanks for joining me on this explainer, and keep optimizing.